new seminar in the Instituto de Astrofísica de Andalucía, Granada, in Spain. And today we will have the talk by Dr. Jesús Miguel Jáquez Domínguez from the Instituto de Radioastronomía y Astrofísica, UNAM in Mexico. And he will talk about synthetic new generation VLBA observations of ionized gas in massive protostars and future prospects for protoplanetary disk studies with the new generation VLA and SKA. So I will pass the word to Dr. Guirado in the room. He will introduce properly the speaker.
Thank you, Dr. Dufar. I'm very happy to have here, we're very happy to have here today Miguel Jáquez. He's from Mexico, from one of those places with a very beautiful name for us, Zacatecas. It sounds really great. And Miguel studied physics and started doing his master's in the IRyA, Institute for Radioastronomy and Astrophysics in the UNAM, the Autonomous University of Mexico. He was working in radiative transfer modeling in the post-processing of hydrodynamic simulations to generate synthetic observations for infrared observatories. He completed his PhD very recently, in June, at the same institute, and his dissertation was focused on radiative transfer modeling of ultra-compact H2 generated synthetic images for the ngVLA. And these days, he's a postdoc working with Carlos Carrasco at the same institute, and his research is focused on the polarization properties of protoplanetary disk. So he's here as a Severo Ochoa visitor. In principle, he's invited by the scattering group, the Cosmic Gas Laboratory group, because it is an interesting research, we thought, and it's been so far trying to use the single scattering properties of the actual real particles that are measured in the laboratory to put them into the radiative transfer model he's using. But there are lots of connections in the institute that Miguel could do, and I think that would be very, very good for all of us. In several groups that I see here, I'm very happy to have it. So after the talk, probably you will find the connections, and we could still have Miguel with us for 5 weeks or 6 more weeks. So we have time to connect and try to work with him. So, yeah.
Thank you for the presentation. So, as Danny mentioned, I am actually a postdoc in Morelia, in Mexico, with Charlie, with Carlos Carrasco, who is a common visitor here. So, first, I want to thank to the Institute and the Severo Ochoa project to give me the opportunity to stay here in this research stay in the institute, and the opportunity to know the Granada city. So let me start with a brief outline about the talk. So the talk is star formation and protoplanetary disk using interferometry, and especially interferometry with the ngVLA and the SKA observatories. There are 2 new observatories that are developed in these days. I show you some of the pipeline and the results from my last work, my PhD work, and how I am studying the disk properties with the CODU lab, and how we can observe these properties of the dust in the protoplanetary disk with the ngVLA and the SKA. But first, let me, as Danny said, let me give you a brief commercial. I am from Zacatecas, in the central north part of Mexico. That is a Baroque city with very similarities with Granada, very small streets, the beautiful downtown, and is one of the first cities founded in Mexico. And then for the PhD, I moved to the IRyA, to the Institute of Radio Astronomy and Astrophysics in Morelia, the UNAM, where is also a beautiful city, and where one of the most beautiful events in the world is happened. That is the Dia de Muertos in November. And also from November to February, the butterflies came from Canada to pass the winter in Morelia, and it's a beautiful spectacle. So, okay, now let's start with the science. So I am studying the star formation in many wavelengths and also in many scales, but the big picture about how the star forming is that the stars begins their life like very dense and cold gas in the molecular clouds that are these big clouds that in the optical we see as dark features. But when we move to longer wavelengths, like in the infrared, we see all the dust that is bright in these regions. So in the dense part of these molecular clouds, that is colored cores, is where the star forming begin like a single object. But the cores are very dense, and then the photons is very difficult to leave the regions, and to observe them, we need to go to even longer wavelengths, like the radio ones, the millimeter and centimeter wavelengths. So for that, we use ALMA and the VLA, that are two radio observatories. But we have another problem. These regions are very, very, very small. So to observe them, we need to use a technique that is called interferometry. Inside this course, the lives of the stars, of the protostars, begin like a core that is collapsing by its own gravity, like we can see in the left part of the presentation. Then the densest part start to collapse faster, and by the angular momentum observations, form a disk of accretion. This disk start to fit the protostar, and in some point we need to extract the angular momentum to be able that the material fall into the protostar. So we can see these outflows or jets, bipolar outflows that are exit from the protostar. So depending on the regime of the mass of the protostar, we will have two paths for the star formation. In the high mass, in some point, even when the accretion is not stopped, the protostar start to burn the hydrogen, and H2 region are developed. So this hypercompact H2 region or compact H2 region is gas that is crossing the ionization front and still accreting to the protostar, but now like a ionized gas. So we can observe this gas by the free emission and also by the recombination lights that are in the radio wavelength, and at this wavelength become transparent to the entire envelope of the protostar. So the outflows, the bipolar outflows, also can extract this ionized gas, and we can observe it like a jet, radio jets in specific. So in the other regime of low mass star formations, the protostar don't make this ultracompact H2 region, and instead we can form the protoplanetary disk in the absence of these outflows. So first, I will talk about the synthetic observation that I am doing in the high mass regime, and then I will talk about the low massive star forming in the protoplanetary disks. So as I told you, the ionized region are very small. The compact is very small, and just some closest region are able to be observed and resolved in morphology and also in kinematics. So, for example, we have the radio jet of the SFA that is observed and modeled by Carlos Carrasco and Charlie, which is one radio jet that is developed by a protostar of 50 solar mass, protostar. And about the ionized disk are only resolved and observed in around a protostar cluster. So we are not observed this ionized region yet in a single protostar. So the question is, the ngVLA could be resolved, the morphology and the kinematic of the radio jet, and also by a ionized disk in a single protostar. So that was my work from the PhD. In the low mass, we want to see if the ngVLA and the SKA could observe all the features that ALMA are observed in the radio, in the protoplanetary disk. And that is the second part of the talk. But first, for the ones that are not familiarized with the interferometry is a technique to make or simulate observations with a telescopes with aperture, with very big aperture. So the idea is make the interference between two antennas that are separated very far, and simulate and then make images from the interferometry techniques to create observation with very high resolution. But we have a very big problem because radio interferometry basically simulate a single dish, but a single dish with a holes, very big holes. So the instrumental response of the PSF, the point spread function of this kind of instrument is very poor. So in order to make better observations, we need to do the interferometric observations with very many antennas. And that is the reason why we construct these interferometers like ALMA and the VLA with very fancy shapes and with many antennas separated in different bases. That is the distance between two antennas. And another big advantage of this technique is that we can construct observatories with the size that we want and the sizes we are able, like the Event Horizon Telescope. Okay, so as I told you, like an interferometer C is just the visibility. The visibility is the Fourier transform of the brightness in the sky. So we need to sample, as is called the UV plane, where the visibility lives, and if the UV plane is best sample, we have best observation. To do that, we construct, as I told you before, this interferometer with many antennas, and also we use the rotation of the Earth to make more and more visibility observations. So this is the technique that the ngVLA and the SKA will be work. So for those that don't know, these interferometers that I told you, the ngVLA and the SKA, the ngVLA will be the next, the evolution of the VLA, the very large array, that is in the south, in the USA. But now the ngVLA, the next generation, we have more like more than 300 antennas that will be distributed in the north of Mexico, the USA, and Canada. And we hope that this instrument will have 10 times more sensitivity and more angular resolution than the actual VLA and ALMA. So this is expected that the ngVLA start to work in the 2030. And one of the key science goals is to study the formation of planet systems at a millimeter wavelength. In the other hand, the Square Kilometre Array is in the south of the planet, and in the mid configuration, we'll have single-dish antennas, like 200, that will work in the centimeter wavelength. So both the SKA and the EVLA and the ngVLA will be to improve our understanding about the star forming process and protoplanetary process, because with ALMA will be covered from the microns to centimeters wavelength. Okay, let me talk about some of the results and the pilot about how to create synthetic observations. And this is the results of my last paper that it was published in February, sorry. So in this paper, what we do is take the model that best fits to the observation to Charlie and create the ionized jet. Also, I also take a ionized disk around a massive protostar, and we simulate the observation with the ngVLA. So for the ionized jet, Carlos Carrasco found that the best model that fit the observation is a conical wind that born very close to the protostar, and in some point, in larger distances from the protostar, a ionized jet, a very collimated outflow, is injected, and this is what Charlie observed. So we simulate this using the Reynolds outflow model, where all the parameters, the essential parameter of the jet, are power law of the distance, and in some cases, in some properties, that is the isothermal, fully ionized, and constant velocity that we expect from the radiojet. The entire model is just described by the accretion rate. So we can use this model to make the radiative transfer model, and we use the same parameters that Charlie found for the jet, and then the wide angle or low collimated wind is injected very close to the star at 3 IUs, and the standard jet is collimated at 55 IUs. So the idea is that we don't know in these days what is the process of the collimation of the jet. So I don't know if we are the magnetical fields, or there is the interaction between the ionized gas that is developed by the protostar, the interaction with the envelope that is still falling into the protostar. And the other model is the ionized disk. So we suppose that the envelope is falling into the protostar. At some point, the envelope is develop a disk, and like the protostar start to burn the hydrogen, the closest center to the protostar will be ionized. And for this disk, we use a single disk model that is defined by the properties of the central protostar, a 20 solar masses protostar, and is defined by the accretion rate also. So the pipeline to generate the synthetic observation is the following. Once we have the ionized gas distribution, we use code to make the radiative transfer. Then that we know the bright distribution in the sky of that will have this kind of object, we pass how this model will be observed by the interferometer, in this case, the ngVLA. This is necessary because the synthetic observation will include the PSF of the instrument, also the noise, and many other instrumental properties that we need to deal with that. And finally, we make two synthetic observations, one for the continuum emission of the free, and the other one was for the recombination lines of the hydrogen in the radio regime. So the output will be a data cube. It's a brightness distribution at different wavelengths that give us a lot of information. Between the information, we can use the zero moment map to trace the amount of gas that is in each region. Also, we can use the first moment, that is the emission integrated in the wavelength or frequency or velocity, that gives us the radial velocity of the gas. And the second moment gives us the velocity dispersion in each pixel. So we use this to make the analysis from the synthetic observation. And what we found is that the ngVLA, we could resolve the kinematics and the morphology for a radio jet like Cepheids 8. And this is, we can see this from the first moment map. That is the third panel in the first image, where we can see the very low collimated wind that is very close to the protostar. And at some point, we see this high velocity jet in the two components, the one that is close, that is pointing to us, and the one that is pointing out to us. And we can resolve the velocities, so we can see which gas is moving at each velocity, and also we can define the position of the injection zone. So this is very important because the different models predict different injection radius. In the ionized disk, we found that the properties of this disk that we simulate, we will have mass emission. So this mass emission is like the laser emission, but in millimeter wavelengths. And this helps us to observe this kind of object very well with the ngVLA, because the emission is enhanced. Also, with the ngVLA, we could resolve the kinematics. Then, resolving the kinematics and the morphology, we can know with very precision the central mass that is forming this ionized disk. Also, we play with the parameters of the models to know what are the finest objects that we could observe with the ngVLA. on also the farthest one. And we find, for example, for the radio jet, that we could observe a radio jet that is driven by a five solar masses. And for example, for the disk, we put the object very far, like 4 kiloparsecs, and we still be able to resolve them. So this is the best. Okay, and now my current research I am doing in the postdoc, and I am doing here with the principal question, that is how the planetesimal particles with a kilometer size are forming in protoplanetary disk. So we know that the big particles in protoplanetary disk tend to localize in the midplane, but many processes we know, because we live in one planet, we know that planets must be formed, but we don't know what is the exactly process that make that micron-sized particles, those particles become pebbles that are particles of centimeters, and these pebbles stick together to create planetesimals that are the core of the planets. So we can use observation to define some properties of the grains in the disk, but recently we are finding that the emission of protoplanetary disks are polarized, and the polarization gives us a very high sense about the size of the particles that live in the protoplanetary disk. So this is what I'm doing right now, because in the last year, many works are revealed that the different properties in the shape of the grain dust can change the properties in the single scattering matrix. So if we can change the properties of the scattering, we can use porous particle or biggest particle to compare the polarization that we are receiving with the polarization, with the models of the particles with the polarization that we are observing. So during the last weeks, I am working with those samples from the CoduLab group here in Granada. We are taking the single scattering matrix from different samples of dust, and I am doing the radiative transfer with RADEMC. So RADEMC basically what do is follow the photons that are emitted in the midplane of the disk or in all the disks essentially, and how change the polarization between the scattering, between the light is scattering by those grains. And finally, we have obtained the maps of intensity, the stock parameter, the polarization, and we know and then we can compare this one with the real observations. So the idea is the work that we will do here is take different samples in different parameters on different types of grains, like prism, also the CoduLab laboratory, the aggregates that we are seeing. This is kind of dust that we can find in the interstellar medium, and also I repeat the process with particles, spherical particles, but with different polarization, with different porosity parameters. So I am doing a catalog of synthetic observations, but when we are varying the different parameters in the dust and also in the disk. So the last part of this research is once we have all the observations, I will pass to the SKA group here in Granada to make synthetic observation, but also synthetic observation of intensity, but also synthetic observation of the polarization parameters in the protoplanetary disk. So with the sensitivity that we expect from the SKA and the ngVLA, most of the protoplanetary disk will have different features and very complex features that we expect. And this is a challenge because the current way in which we make images from interferometry are able to recover very, very fine morphologies. So in the last part of my visit, I will work with the VLBI group in order to apply the techniques that they use to make the black hole pictures, to observe, to apply it to the synthetic observation that I will create from the SKA and the ngVLA observation. And this is all. I give you some take message about the importance of make synthetic observation, and I'm happy to answer any question. Thank you.
Okay. Anyone want to start?
Thank you for this nice talk with a very nice overview.
Thank you.
I have many questions. At least three for the first part. It seems to me a little bit weird to have in CPs only start with high solar mass. I was thinking that the central start would be around 10 to 20, even 20 solar mass, because as far as I know, this solar is able to excite high ammonia inversion transition. No? Perhaps there are something wrong in the models, in the assumption, because I have seen that you are assuming a lot of power load to constrain the density, temperature. Perhaps if we use the ammonia data, you can constrain better these properties and infer a better determination for the central mass.
Yes. This work is just for radio combination lines of the hydrogen. So if we have more information about the transition, we can constrain better the properties of the radiojet, for example, or the ionized disk. And this is just an approximation, like everything in astronomy. But the idea is to test if these interferometers could be resolved in ideal way, this kind of properties. But just and for the models that I present, the jet is powered by 15 solar masses protostar, and the disk is for 20 solar masses. So maybe if we move to the lower masses, the observation will be more difficult in all the sense, no? Because we have less ionization fraction, for example, or maybe the jets don't be so powerful to make it in a constant velocity. The idea is passed now from, this is for analytical simple example. The idea is do the same, but with the hydrodynamical simulation, more realistic hydrodynamical simulation.
Back on the ammonia inversion transition that Charlie had been reported very recently, because they will be difficult to constrain these properties, in particular the density and temperature reached by the disk. Radiating is polygonal
Yeah, sure.
And I ask another question related also with the second part. It's very important to constrain for the loss properties, the size is the loss, the abundance, the composition. But I guess an important, again, to do that, one important thing is to constrain also the density and temperature. How, I guess, to constrain better the dust properties, we have to constrain the first, the dust, the temperature, and the density, perhaps velocity of the substructures of the environment of the dust around the young star. Could you mention some words as far as I hear here? You will assume overload, but I encourage you to use more self-consistent model, taking advantages, many observations to concentrate the whole picture. No? And the second question is how you will do with the Square Kilometre Array, because it will operate mostly in centimeter wavelengths where the emissions drop very fast. I guess in the sense it will be better the new implementation.
Yeah, the idea is try to see first the polarization features for each model. Depend on the inclination of the disk, the density distribution, and the particles that we are assuming. And then this is just a power law models, but now we are trying to make a collaboration with people that have simulated all the chemistry of the disk, the radiativity transfer to know the temperature distribution, and so on. So that is a second part of that project. And sorry, the question. The second one.
First, my point that is very important to constrain the density and temperature to start to find out those properties or to constrain all the physical properties simultaneousness in a simultaneous way by using many observational constraints and also self-consistent model. But my second question was about the Square Kilometre Array, no? Which is we will operate in the centimeter wavelengths mostly, where because you know we have already mentioned the dust emission drop in different rates, and yes, it will be better to use the new generation, and also because in the centimeter wavelength we have another mechanism. For instance, if the emission for the reason is difficult to use the wavelength because they those properties. No? And this will have a different idea about this. Can you comment about this point?
Yeah, for example, yeah, is with the SKA will be very difficult because the low emission from the dust particles. But okay, until now, we want to make the qualitative properties from different grades in simple models in order to increase the realistic in the models. We are the base for to say that, and we can make some models about the free emission that we expect, about the emission of the disk that we expect, make the synthetic observation, and maybe we can extract the contribution to each kind of gas that we are seeing, or dust. But maybe that will be more difficult. And the ngVLA is just don't observe to centimeter wavelength, so the SKA is the only that we can have. Maybe in the closest protoplanetary disk, we can make some observations, but I need to make the synthetic observation.
Thank you for the nice talk. I have many questions, but I am particularly intrigued with about one of your comments that I understood. Are you able to predict the major emission of the disk? Or
Yes.
I misunderstood something?
Yes. In the disk, we see that the radiative transfer model predict the mass emission.
Which mass emission?
Is for the H38 alpha line of the radio.
Okay. So you are not predicting molecular emission.
No,
emission,
it's
like water,
just ionized gas.
So you are predicting that the radio combination lines are have a major contribution.
Yeah.
Okay.
Sorry.
Okay. Now I understand now your point. And regarding the radio combination lines, are you taking into account the inclination of the jet?
Yes, it's the inclination and the inclination is taken.
You find very broad line, which is the width of the line you predict, because the typical problem with the recombination lines, and this is the main reason why they have not been detected yet in the jets, except one case where they are maintenance side, is because you have something that moves very fast, like a jet, 100 kilometers per second. Your line emission is distributed over a very broad range of velocities. So your intensity is very small, and they are very difficult to detect. We predicted, this is very documented in several radios we have done, that they would be detectable with the Square Kilometre Array, probably with the new generation ULA. But I was intrigued about which is the width, because apparently you have done a much more complete model of the radio combination line.
Okay, now I don't remember the broad of the lines, but in this observation we are using the total broadband of the ngVLA, that is 20 gigahertz, and we could resolve the lines from the central part that is moving slow, and from the radio jets that is moving fast, but I don't remember very well that number.
Well, it was intrigued about the intensity and the width, because these two things go in the opposite side. So you obtain very broad lines, they would be very weak, probably undetected.
Okay.
It was a curiosity.
Yes.
And also, probably you know that the radio combination line has the property that they are at regular frequency, so they can be stacked, and then you can get sensitivity and improve the sensitivity. But you can stack several lines shifting in frequency, and then you can reach a detection with regular technique for you. Okay, thank you.
Miguel, the polarization is the most interesting part for us from the core lab, because there are lots of single scattering properties depending on the polarization. Now we see how they translate in putting them into the radiative transfer. But I'm worried that we are measuring size parameters in the range of 10. So, the question about the big kilometer particles in the protoplanetary disk, which is we don't know how they form, are a little far from that. So what would you need for this kind of simulation or probability transfer modeling in order to answer those questions from the side of the single scattering properties of the particles? Could be measurements, could be calculations, modeling. What size compared to the wavelength? Now that we will have SKA, for instance.
Which size?
Those wavelengths will be.
Uh-huh.
You had some plot there with.
Or in which?
Because I don't know if we are in the range or not to give you what you need to put in the modeling. Kilometer,
Yes.
particle, and wavelength will be centimeters.
No, the kilometer. Really. 18, if I could do the maths very quickly with the meters.
Meters.
Yeah, in meter wavelength.
Okay, then we have it's like 1,000 with the big particles, millimeter particles with the visible light. Yeah, so those measurements.
Yeah, but also the porosity particles. In spherical particles, the maximum of the polarization or the polarization is doing also in some very small frequencies.
Mm-hmm.
But when we add the porosity, the polarization extends to very large wavelengths. So this is why we need to make the observation in different wavelengths to see to constrain better the grains.
Okay,
Nice.
Yes, the Square Kilometre Array and either the new next generation will be able to detect kilometer size particles. You can infer this indirectly because it doesn't make sense. In this group.
Kilometer size.
Kilometer, I guess it was.
Yeah,
questions.
but kilometer size should be that. No, well,
To detect this.
meters of
I
where?
don't know meters, even meters, but that's 1 centimeter.
If it goes like the wavelength, the -3 over the lows, trembling with each.
No, es que llegó dos down to 15 megahertz, so that would be 10 meters.
No, but the emission is very low.
But the emission is, it will reach the wavelength, but the emission is extremely low at this wavelength. So not even with the idea of the Square Kilometre Array. And the other thing is that you already take into account there is ionization. And the ionization grows. It's very, very strong, and I am completely sure that will dominate fully the emission of these large iron cores. My opinion is not very popular because it's easier to sell planet formation to a kilometer size than something that is contaminated by a lot of free emission, for example. And probably will not have more emission at this very low.
Even in the case of low mass star formation, do you expect very important contribution of free emission?
Because yes, and then, well, you go to more evolved bodies, like Matthew Star, for example, Centauri, and so on. Then there are other phenomena, of course, in the star, but at least this accretion ejection process has already finished many millions ago. But you are at the stage of planet formation. There is still a bit of accretion. A bit of accretion means a bit of ejection. And if there is ejection, there is ionization. And this ionization will probably kill many of these dreams on the detection of these precursors of the planets. Of course, you can reach the centimeter size, you can detect evils, and it's already has been done now. It's not with the emission well resolved. Probably the new generation VLA in the Square Kilometre Array can do. But I think to reach the kilometer size, it's something a very difficult challenge.
Well, if we will find the model for the smaller particles, then we have some idea of how they could form contacts in that sense. Anyone else?
Okay, thank you very much for the